Great.
All right, so hello everybody and welcome to this week's Science Lunch Talk. Today we have our guest speaker, Jeff Iuliano, who is a postdoctoral researcher at the University of Pennsylvania. And he'll be giving us a look at CLASS, the Cosmology Large Angular Scale Surveyor, a telescope array that he has been working on. So everyone, please remember to mute yourselves during the talk, unless Jeff, if you are open to people unmuting and asking questions,
Yep,
or saving them for the end. Okay.
Yeah, please interrupt me with questions if you guys have them, and I'll obviously stop it at the end for extra questions. But
yeah, exactly. So with that, take it away, Jeff.
Sounds great. Thank you. So as Jesse said, I'm Jeff. I am currently a postdoc at UPenn working on a different but related telescope, specifically Large Aperture Telescope for the Simons Observatory. But I'm going to talk today about CLASS, which is what I did my graduate work on and I'm still helping with. So CLASS is, as we said, the Cosmology Large Angular Scale Surveyor. So we'll talk a little bit about what that means. But basically, it is a cosmic microwave background polarization survey. So I'm going to talk a little bit about the CMB, about cosmic inflation, and why polarization of the CMB in particular is something we're interested in. And then I'll move on to CLASS specifically, because there's a number of CMB experiments. And so the question is, what makes CLASS unique? What's our approach? How do you actually build this instrument to accomplish what we want? And then I'll focus a little bit on the cryogenic receiver, which is what I spent a lot of my time working on, and is one of the primary components of building a telescope. And then we've been observing since 2016. So, here in 2021, we are now publishing our 2-year results. That's how that goes. That's actually very exciting, actually. We can start to show that the instrument works. Okay, cool. So this is the history of the universe. Many of you may have seen this before. And so because we are studying the cosmic microwave background, we are looking at this over here, right? The CMB is the glowing light from the very early universe. And then we're going to touch on 2 other key time periods, which are inflation and reionization, when the first stars turned on a few 100 million years later, because both of these are things we can learn about by looking at the CMB, right? So if you look at this picture of the history of the universe, right, you can see way back early on, the universe used to be a lot smaller, and because it was smaller, it was denser, it was hotter, and it was just filled. If you go that far enough, you reach a time where it was hot enough that it was filled with this plasma, right? It's just hot enough that everything was ionized and that glows, right? So we can actually still see that light. If you look deep enough into space, you'll eventually get back to that glowing plasma. And that's actually the oldest light in the universe, right? Because it was opaque, you can't see past it. This glowing plasma, which is a very nice black body, then the light from that gets stretched as the universe expands going forward in time. And so now we see it as a microwave background, which we can study. So it helps us learn about the very early history of the universe because it is the oldest light in the universe. And it also tells us a lot about what's going on in the universe since then, because it traverses the whole universe to get to us. Cool. So if you take a look at the CMB, which people have done, you'll see something like this. And so you might ask the question, why does the CMB have this particular shape or pattern, right? You can see it's fairly uniform, but there's these anisotropies, sort of famous hot and cold spots that we've been studying for a few decades now. In order to explain that, it's useful to introduce the idea of cosmic inflation. So this is really a family of theories, but the basic idea is that early on in the universe's history, right, just fractions of a second after the Big Bang, the universe expanded massively, almost instantaneously. It went from the size of maybe an atom to the size of a galaxy in a tiny fraction of a second. Now, this is a pretty sort of extreme idea if you think about it, right? That's a pretty violent behavior we're saying the universe underwent, but it explains a lot about what we see in the universe around us. It explains why the CMB here is fairly uniform, and as I'll get into in a second, it explains why it has these sort of anisotropies. It explains why the universe looks flat, and explains why we don't see magnetic monopoles. It does a lot to explain things that otherwise don't have explanations just with the standard Big Bang cosmology. So like I said, in particular, one thing it does for us is it sort of gives us a reason to think, to know why the CMB has these little non-uniformities, right? So if you have, quantum mechanics exists, and because of quantum effects mean that you never are totally uniform, right? You're going to have small quantum fluctuations. And then when inflation happens, those small non-uniformities at the quantum scale become stretched into like macro scale phenomena, right? So remember, we went from the size of an atom to the size of the universe almost instantaneously. And so you just don't get a perfectly uniform distribution of stuff when you're done doing that after inflation. And so that leads to actually just areas with more dense like matter energy in the universe and less dense matter energy in the universe. And that ends up creating the hot and cold spots you see in the CMB. This also happens to like space-time itself, the gravitational field. And those non-uniformities are gravitational waves. So this is actually a real prediction of inflation. Remember, I talked just a couple slides ago about how inflation makes a lot of sense, even though it's kind of a crazy idea because it explains a lot. Well, the existence of these gravitational waves is now like an actual prediction instead of just explaining something. So if we could see evidence of these gravitational waves from the early universe due to inflation, that would do two things for us. It'd be really good evidence of inflation, which is good, but also could help us characterize inflation because there's lots of models you could write down for how it happened, why it happened, mechanisms, whatnot. So if you can begin to parameterize inflation, that's really helpful. And it's one of looking at the CMB in order to understand these gravitational waves is one of the very few like empirical tools we have to actually understand inflation. So that's a big deal. So the way we do this is we look at what's called the tensor to scalar ratio, R, where the tensors is the gravitational wave component of this sort of anisotropy, and the scalar is the density component, right? So if you just take the ratio of those amplitudes, you get this factor R, which parameterizes inflation. Okay, so if we could see these primordial gravitational waves, that would be really useful. We can't actually measure them directly. I know people do gravitational wave measurements, but these would be way too small and long wavelengths to measure directly. But we can see their effect in the CMB through polarization. I think there's supposed to be something there. Oh, well. So let's talk a little bit more about what actually happened when the CMB was forming, right? So we had this hot plasma in the early universe that was glowing. Because it's a plasma, it's also opaque, right? Light bounces off of the electrons that are floating around and has a really short mean free path instead of acting as one thermalized soup, right? As the universe expands over time and cools, eventually you start to cool to the point where the free protons and electrons can form neutral hydrogen. This makes the universe rapidly become transparent, and then light kind of free streams to where we see it today, and that is the CMB. But you can sort of see you have a scattering process that is going on and becomes transparent. And as with many scattering processes, if you have any asymmetry, you can generate polarization, right? You see light reflecting off, a lake here, you get polarized light in a sort of a similar way. So specifically, if you think about an electron sitting in the CMB, right? You have on the square on the right, sort of maybe a zoom in on that on a map of the CMB where you have the hot and the cold spots. And so that's really just a picture of some plasma, right? And you have an electron sitting in that plasma and a bunch of light coming towards it. And then some of that light bounces off the electron and comes to us today, and that's the CMB. And so if you remember, one of the key features of light is it's a transverse wave. So if you're this electron sitting in the middle here, and you have light coming from the left and light coming from the top, only one part of each of those incoming electric fields can actually scatter towards the Earth, because you can't scatter the longitudinal direction, right? Which basically means that the orange and the blue amplitudes are not the same because there's some asymmetry in the environment of the electron. You're going to end up with an asymmetry in the horizontal and vertical electric fields coming to Earth, and that's just polarized light, right? And so we get some small polarization in the CMB because the environment of the plasma is not totally isotropic, right? If you imagine sitting as some electron in the boundary between this hot and cold spot, right, you're going to see brighter light coming from the hotter region and less bright light coming from the colder region. And so you're going to see this kind of same asymmetry that leads to CMB polarization. Interestingly, gravitational waves have a similar effect, right? A gravitational wave is this distortion in space-time that's propagating. And so if you had a ring of particles, it'll do this it'll turn this ellipse and then this other ellipse you sort of see in this animation here, right? That's going to actually, because it's compressing and stretching space a little bit, it's going to redshift and blue shift light, and it will create the same kind of asymmetry and lead to polarization. So we expect some polarization in the CMB. We expect some of it just because of the hot and cold spots we already know. We could predict some polarization from that. We could also expect to see some polarization from gravitational waves that would be really nice to study and find out about, right? So how do we tell the difference between these sources of polarization, right? If we want to use a CMB polarization as a way to understand this, we want to be able to separate those effects. Well, one way to do it is to describe the CMB in terms of what are called E modes and B modes, right? You see this map on the right is a map of the sky. I mean, you can see the galaxy really clearly there, but the lines on the map are basically the orientation of the polarization at each point in the sky. And you could describe that map just in terms of how, where it's vertical and where it's horizontal, right? That is instrument specific, right? Or choice of axis specific. You have to pick how that's oriented. So one nice way to do this is to split it into the sort of like curl-free and divergence-free patterns, right? You sort of have the sort of topological looking thing in the E modes and the spiral looking thing in the B modes. That's really nice because it's sort of orientation independent. What's even nicer about it though is that while gravitational waves will make E modes and B modes, the like hot and cold spot, the density fluctuations in the plasma will only create E modes. So that means if you see B mode polarization, you know it's from these primordial gravitational waves. And then you can pull out R. It turns out the density perturbations are enough bigger that they're going to really dominate the E modes. So like roughly speaking, R is the ratio of the B modes to the E modes. So to summarize, if we want to understand inflation, we can predict that it will create primordial gravitational waves, and then those gravitational waves should create B mode polarization in the cosmic microwave background. So if we can study the polarization of the CMB, we can get back, or at least one thing we can get back is the characterization of inflation that we're really looking for and some evidence for it. Now, like I said before, we also learn other things from the CMB. So, it's not just inflation, but this time reionization when the first stars turned on, that reionizes some of the light, that light reionizes some of the gas in the universe, and now you have some free electrons again. Some fraction of the CMB photons that are traveling through the universe scatter off those free electrons. And so reionization and like when it is and how it happened imprints some pattern in the CMB polarization that we can see by looking at the E modes actually. And just sort of in general studying this, because we're looking way, way back to the early universe where things are very hot and the energy scales associated with inflation, for example, are extremely high. And so like we just might see surprising new physics because we're sort of pushing the boundary at which our physical models even like we think we believe them anyways. So great. So that's sort of like the first bit. That's sort of why do we want to study the CMB polarization? What can we learn from it? And like, what are our goals? So I'm going to move on to now class specifically and our approach to doing this. So if you have a map of the CMB, right, you guys showed that to earlier, you can like stare at it and you can sort of pull out the baryon acoustic oscillation peak, right, the little sort of 1-ish degree peak by looking at it. But really, if you want to understand it, a useful thing to do is to make a power spectrum, right? So it's basically like a Fourier transform, but where you use spherical harmonics instead of sines or cosines, and you get back a nice sort of summary of what is going on in your map. So you can see on the left here, right, the y-axis is how much pattern there is, and the x-axis is what angular scale you're looking at. So further to the left is large angular scales. And a couple things that I want to highlight sort of in this plot, right? The temperature anisotropies, like how non-uniform the temperature pattern is orders of magnitude greater than the E modes. And those are even a few orders of magnitude stronger than the B modes. So in order to see the B mode polarization or even the E mode polarization, you really need a sensitive instrument. The second thing though, is if you look to the left, the pattern is greater, right? There's more non-uniformity at large angular scales than small angular scales. There's also this effect where gravitational lensing can take E modes and turn them into B modes, and that is a bigger effect at sort of mid to small angular scales instead of the really large ones. So the B mode, like the primordial B mode signal may be actually greater relative to the lensing at large angular scales. So if you could build an instrument to study these large angular scales, that could be a really good way to get at this pattern. You have another problem, which is that the galaxy exists and also has in-band radiation, right? So you need to do something to remove that, right? So you can see here the CMB's peak is maybe around 100 gigahertz, but there's, you can just see the galaxy if you make a map of the sky in that. So you need to be able to remove this to get rid of these foregrounds and get back to the primordial CMB signal. Fortunately, the galactic sources are like not black bodies at the same temperature as the CMB. Right? You have synchrotron emission at lower frequencies, and then you have dust emission that is dominant at higher frequencies. So if you make a multi-frequency survey, you can remove those and get back to CMB. So class needs to be very sensitive, and it needs to look at large angular scales, and it has to span some number of frequencies to remove the foreground. So this plot just kind of summarizes where class fits into that sort of parameter space. We're looking at large angular scales across a certain range of frequencies. And so not only is I think that a very useful parameter space, like place to be to look for the B modes, it also sort of is very complementary to a bunch of other CMB experiments that are taking different approaches or looking specifically at the small angular scales because there's really interesting science to do there. So that's really a cool thing about class. Okay, so we need a very sensitive instrument, large angular scales, and we have actually 4 telescopes spanning low, middle, and high frequencies, where the middle is like the CMB channel and the low and high help with the foreground removal. So what do we do this? We observe from a mountaintop in northern Chile. This is nice because it's accessible by the road, and you can see a lot of the sky. It's also very high and very dry, so you have less of the atmosphere, in particular water in the atmosphere, in your way. So here we are, high and dry. So there's, like I said, 4 telescopes, 2 go in each of those mounts. So let's open that one up, and you can see sort of 2 telescopes right there. You can sort of partially assembled. Let's cut that in half. And now let's going to talk a little bit about parts of the instrument that sort of make this whole thing work. So the first is our modulator. What this does, the variable delay polarization modulator, VPM, as I'll talk about it, is actually like what lets us do this from the ground, looking at large angular scales. One problem you have, actually I'll go to this side first. One problem you have is that as you scan the sky, you're going to scan across the atmosphere and your instrument might drift. And there's all these things that affect your signal that are not the polarization. Remember, the polarization signal is very, very small. And so if you wanted to be able to compare the left on the sky to the right on the sky, you need your instrument to be very, very stable. And so what our modulator does is it actually lets us lock into just the polarization signal. The way it does this is it's like a wire grid. We call it a grid, but it's really a bunch of parallel wires, and there's a mirror behind it. And one polarization bounces off the wires, the other one passes through the wires and bounces off the mirror, and it travels that extra path length. And that extra path that travels depends on the position of the mirror, which can move. So what this does is, depending on where the mirror is, it can turn linear polarization into circular polarization or not. So this effectively, because our detectors are only sensitive to linear polarization, not just circular polarization, effectively turns the polarization signal of the sky on and off. So you see this, like, say the mirror is moving back and forth at 10 hertz, you see this at a 10 hertz modulation signal on top of your bigger drifts. And if you just lock into that 10 hertz signal and demodulate, you get back just the polarization, and you can remove the big temperature drifts that otherwise would totally swamp your ability to see these large angular scale modes from the ground. Our detectors are obviously a critical part of any sensitive telescope. So here you can see we have 3 different detector arrays here, with the 4th one coming sometime this year. We'll be deploying it. You span the different frequency ranges. Our detectors themselves are what are called transition edge sensors. So this is basically, you take a superconductor that will transition from normal to superconducting around, say, 150 millikelvin. And when it's on that transition, its resistance changes really rapidly with a small change in temperature. So if some photon hits it, from the CMB, its resistance changes a bunch. And so if you put it in a circuit where you can measure that changing impedance, what you have is a really sensitive detector, and then you just amplify the changing current in that circuit as you read it out. Okay. So finally, you have the receiver, which is sort of the heart of the instrument here, where the detectors live. The job of the receiver is to keep the environment for the detectors very cold, very low noise, but still let a lot of light reach them. So if you want a very sensitive instrument, you need a very high signal to noise. So high signal means as much of the incoming CMB light that hits your telescope reaches your detectors as possible. And then low noise means basically you need a very cold and stable environment. I won't read all of this, but basically the sum up of it is that you need to stay below around 100 millikelvin, and the class receivers achieve about 50. So how do you do this? Well, first you need to put the whole thing inside of a cryogenic, like a cryostat, right? You need a cryocooler to get you that cold in the first place. The very sort of basic way you do that is you start with separating your instrument into different stages to sort of insulate and get down, so step down to lowest temperature. So we have our room temperature outer stage, about a 45 Kelvin stage. And so each of these is totally encapsulating one inside of it, right? So there's a 3K stage, a 1K stage, and finally your 50 millikelvin stage, where each layer is helping reject heat from the outside to keep the inside bits cold. Also keeps your optics cold too, which is nice. So to do this, we have a two-step cooler. The first is a pulse tube. This works kind of on the same principle that most coolers we experience do, right? You take some gas, you compress it, it heats up, you dump that heat to the room, then you uncompress it and it's colder and it pulses. That's why it's called a pulse tube. You can actually hear it pulsing at a little over 1 hertz in the lab. And so this gets us down to a little under 3 Kelvin with, more cooling power at warmer stages and still, a couple watts of cooling power at the colder stage. Once you're down to 3 Kelvin, you need to move on to what's called a dilution refrigerator to get the rest of the way. What the DR does is it mixes helium-3 and helium-4 isotopes. And when you have this liquid helium-3 and 4 together and you mix them, just due to the way the phase diagram works out, basically, it takes energy from the environment to do this. And so then once you mix them together, you pump on the other end and helium-3 evaporates more easily. So it basically comes out and you put it back in the other side and mix it again and it gets colder. So as long as your pump is on, you keep mixing and mixing and mixing this, and it just keeps getting colder and colder and colder until the base temperature of around 50 millikelvin. So that has maybe a few hundred microwatts of cooling power at the 50 millikelvin stage. So this is sort of the fundamental problem of building a telescope. As soon as you open up the end of your telescope to the room or the sky, you get about 70 watts of power, and you have 300 microwatts at your cold stage. So you have to cut the incoming power, and I don't mean from the CMB, I just mean like radiative power from infrared emission in the sky in the room. You have to cut that by a factor of about 1 million. At the same time, you want to let as much of the CMB light through as possible. Anytime you lose CMB light, that's, you lose signal. So class does this, and we lose less than 1/4 of our in-band light to the optical elements, the lenses and the filters. To achieve this, we have this series of filters that we insert into the cryostat that have sort of been carefully designed, like which goes where. We've did a lot of work to figure out how to do this just right in a way that sort of is optimal. So one kind of filter is an insulating filter. These are actually literally styrofoam pieces that we cut in a CNC machine, and they act a lot like insulators. They absorb the infrared light and then re-emit it either out the front of the cryostat or to the walls where it gets conducted out through the coolers, and then the CMB light passes through. You also have conductively cooled absorbers, these are pieces of Teflon, and they absorb this, again, the heat, the infrared light, and they conduct it out directly to the sides of the cryostat, and the CMB light passes through. Finally, you can use reflective filters. We've actually moved away from these a little bit because the insulating ones work so well, but same idea. You reflect the infrared light and let the CMB light pass through. You put that all together, you have a full filter scheme, and this is our 90 gigahertz instrument. You can see we have a bunch of foam, some absorbing lenses, and whatnot. And then on our HF instrument, after actually working at this longer, we figured out we could move to a filter scheme that really is built around these foam filters because they're nice because they're very, very low loss, right? The other ones you have to add anti-reflective coatings to keep you from losing the CMB light. With the foam, it's so low density, it's basically transparent. It's basically transparent. So we really, our more recent receivers have moved to using those more than the other ones where we can. But in the end, this all works really, really well. We lose very, like I said, a small amount of our CMB light to absorption and reflection here, and the cryostats stay cold out in the field. So here you can see there are 3 different designs, right? The 4th telescope is just a second copy of the 90, where we've maybe slightly updated the filter scheme to match the high frequency one here, but they're all very similar, right? The changes are basically frequency specific things about where baffles go, or the optical design has changed a little bit to accommodate for that. So the other things your cryostat has to do, right, to as the camera for the telescope, is it has to maintain optical alignment. So we do a bunch of work as we're assembling this to make sure all of the supports keeping this sort of cantilevered horizontal shape out there are very stiff. We measure the position of everything very carefully, and we achieve something like a millimeter or so precision and over the meter length of the cryostat in putting these lenses in place relative to the detectors. You also have to control stray light in your cryostat. So, we add all these blackened baffles where we put this carbon loaded epoxy on the inside to absorb stray light and control reflections. And we end up with very nice beams. And so, yeah, you do all that, you put it all together, and then you want to go deploy it in the field. So here's some pictures of us putting our 90 gigahertz telescope together, right? So you put the detectors on, there's a black field stop there to help control reflections. There's the 1K stage going on. There's the 4K stage. Put it all together, then you put it up on the mount up there, and there's that picture we started with, right? So that's sort of how this all comes together. And so having had some of these in the field now, basically we can say that there, I said we had to be below about 100 millikelvin for the to be cold enough not to really contribute noise to our detectors. And we're below that 90+% of the time for the 40 gigahertz. And the other ones, basically when it's operating, it's cold and stays cold. We've had like power interruptions sometimes that like reduce the total fraction of all time that it's cold. But when the cryostat is on, everything works and is fairly stable, which is really, really good. So just I'll wrap up here by saying that we have been working on our 2-year observation publication. So you can see we have a bunch out already. We have the sort of data and results coming up, and I'll just sort of highlight a couple of the things we learned from it. So you saw one of these figures already, but I mentioned the VPM, right? This is basically demonstrating that the VPM allows our data to be very, very stable, which lets us get out those large angular scale modes we were really looking for in the sky. So the VPM is doing exactly what it was designed to do. I maybe didn't mention it before. The VPM is basically a new piece of technology that is shared between CLASS and the balloon experiment Piper, which is sort of a similar design. And right, people use spinning half wave plate sometimes to this kind of modulation. This VPM is a totally different approach that seems to be working very well. It's sort of critical to CLASS's ability to do this. We have a beam and calibration paper. We use the moon actually as a basically point source calibrator because we're looking at large angular scales, we can have a fairly large beam. And so we did a bunch of work calibrating off of that, showing that our polarization measurements are working and mapping out our beam. And so that's working, that's good. One really cool side effect of the VPM is that I said our detectors are only sensitive to linear polarization, but the VPM can turn circular polarization into linear polarization, right? I talked about how it turned the polarization signal on and off in the sky. Well, when it's off, that actually means it's like the whole instrument is sensitive to circular polarization, which we expect there to be basically none of in the sky, but a little bit of a circular polarization signal from the atmosphere. So you can see on the left, the simulated atmosphere signal we actually measured. And then when you remove that, you get back on the right, classes made like basically a new lower bound on the possible circular polarization like in the sky past the atmosphere, which is just a really cool side effect of this design. What's another thing that's really interesting you can do is, we're looking at the CMB, but you can actually do some planetary science with glass. So we observe Venus. I mean, part because it just goes through our, as we scan the sky, because we're making a whole sky map, Venus just goes through. So we have measurements of it, and we're observing at, three different frequency bands, four really, 90, 40, 90, 150, and 220 gigahertz. And the Venus's atmosphere, it's like transparency, its opacity is different in those different bands. And so you can see deeper or shallower into the atmosphere depending on which band you're looking at. And that means that you can use class data to differentiate between different models of the Venusian atmosphere, which is a really cool project we did with this data, which was fun. The real highlight, though, that is sort of the point of all of this, is that the telescope is working. So this is all 40 gigahertz data. So this is not the CMB primarily. This is really going to be sensitive to synchrotron radiation in the galaxy, which you can see really clearly in these maps. But on the left, you see a WMAP map, and on the right, you see a preliminary class map at 40 gigahertz. And the fact that they are very, very similar basically means that what class is doing is working, right? Our telescope is doing what we want it to do. And now that we have 3 observing and we're polishing our pipeline, we'll get the 4th one out this year, we will be able to push ahead with our science goals. And we're really excited to see what we can say in the coming years. Cool, thanks.
All right, wow, thank you very much, Jeff. At this point, we can turn it over to the audience. If anyone has a question, feel free to unmute yourselves and ask away. But while everyone's deciding what they want to ask, I had a quick question for you. Earlier on, you'd mentioned that there were 4 different detectors. You only showed off 3, I believe. What is the 4th? What band is that working at?
Yeah, so our 4 bands are 40, 90, 150, 220. I didn't actually pause and explain this very clearly. So there's 4 telescopes and 4 bands, but they're not lined up the way you'd want them to be to make sense. So we have one 40 gigahertz telescope. We have 2 90 gigahertz telescopes because that's the main science demand. That's where we're really going to see the CMB most clearly. And then the high frequency telescope is actually a 150/220. So each pixel is actually multichroic. So if you zoom in, so that might be like what one of our pixels looks like, where you have the horizontal and vertical like antennas there, and those go off to TESs. You can actually split those waveguides off and send and the way you actually like set the band is with filters in this chip. And so if you split the signal off to like, say you have, the horizontal here, you can, instead of going to one TES, you can send it to two TESs, one with filters to make it 150 gigahertz band, one with filters to make it a 220 gigahertz band. So you actually get multiple frequency channels on the same pixel. And so that's what's happening with the high frequency one. So the fourth one, the one we haven't deployed yet, is the second 90 gigahertz, which looks almost exactly like this. It's basically a copy of this telescope to get more detectors on the sky. With the caveat that we are slightly changing the filter scheme to look a little bit more like the high frequency ones. We decided it worked better. It's just like a little higher efficiency. So we're going to try doing that at 90 for the second one.
Nice, with the potential hope of being able to update the original 90 gigahertz.
Yeah, I mean, it's one of those things where how much downtime do you want to gain like a small fractional increase in efficiency? But the hope is to upgrade all of this in the future with like more detectors. And so any upgrade path would probably involve that.
Okay, great. All right, do we have any questions from the audience? One quick question from the chat asking where the recording will be posted. I can share some more information at the end, but all the videos are uploaded to our YouTube channel. Don't be shy. Anyone have any thoughts that were brought up during the talk? Jeff, I don't know if you have any fun additional bits of information that you
I mean,
have
that
for
was
time.
a lot of information all at once.
It really is, yes.
That's how this goes, right? There's the CMB, and then there's, oh yeah, we built this whole big instrument. I mean, I think really the thing I sort of went by quickly is that there are a lot of CMB experiments. What makes class unique is this focus on large angular scale. Like, and when I mean large, I mean we're getting down from like 10 to 90, like the largest possible angular scale in the sky. A lot of other attempts to see the to like measure this beam mode are focused more at like smaller patches of the sky, going really deep at like maybe 1 to 10 degrees. And so it's just really, it's a slightly different approach that it wasn't obvious you could do this from the ground, but the fact that it's working is really cool to see.
Absolutely. And yeah, you talked a lot about the VPM.
Yes, the modulator. Yeah, VPM.
Yes, which you use for getting rid of atmospheric distortion. How well do you think that does compared to, say, a lot of CMB experiments are airborne, so you're basically trying to get up over the atmosphere, whereas here you're willing to look through it.
Yeah. It's clearly doing what we designed it to do. It has a bunch of really cool advantages and a bunch of like, complexities you have to deal with. But it's fundamentally doing what it was designed to do, which is, the whole point. I mean, the advantage of being on the ground versus the balloon is that you can observe a lot longer with a lot more detectors. So you can ultimately get more sensitivity. Which is nice. I mean, the balloons, because you get above the atmosphere, you can look in slightly different bands. You can look in higher frequency bands. There's like, there's advantages of balloons too. That's sort of why I really like this parameter space plot I was showing, because it sort of shows that covering, looking at this all the ways you would want to look at it involves really a bunch of different CMB experiments complementing each other, rather than strictly competing with each other, which is, I don't know, that's a nice way to view the field, right? Like, you don't want just one end all be all experiment. You want a bunch of different approaches that look at different areas here. So like our sister experiment that also has VPM is Piper. And that is a balloon experiment with this VPM on it. And so it's pretty clear, it isn't just the atmosphere, right? There's like other things you want to pull out. It's really just helping you.
For sure.
Though, I mean, that's from the ground, that's the biggest thing. But, it pulls out the polarization signal from any of the temperature signals, but also like your instrument drifting. And like, if your instrument properties drift over time, you still can't do this large angular scale recovery. So it lets you I mean, so the way you would get polarization if you did a lot of experiments do this, if you don't have a modulator, is you just subtract your horizontal from your vertical, like pairs of pixels and your detectors in one pixel. And that means that those two detectors have to be like very well matched in terms of gain. You have to understand the gain match, how they're matched in terms of gain, and that if the properties drift over time, which things in an instrument tend to, it makes it hard to compare like long time scale effects, right? You can see as you're scanning across the sky, you can see like, 5 seconds, really, you can believe what's happening, but after a minute, maybe you can't compare the beginning and end to, like, amplitudes of those signals to think that they actually, that comparison is meaningful. And the modulator means you can get your polarization from not just from that pair subtraction, and that lets you like do this larger scale thing, even if you don't have the atmosphere in your way because you're Piper. And that's sort of why it's critical for the large angular scale science in particular.
All right, great. All right, I see Michael Barth has his hand up. Before we get to you, Stephen Myers wrote in the chat, can you say anything about your work on CMB S4?
Yeah, well, so I'm not doing a lot for S4 specifically, though I was at the last big meeting. I'm working on Simon's Observatory right now, which is sort of, I don't know how you think about it officially, but like it's basically doing a small scale version of what S4 will be doing, right? SO consists of 3 small aperture telescopes and 1 large aperture telescope, and I think S4 is like that, but scaled up by a factor of 5 or something, including the South Pole and Chile. So we're basically going to like, at least order of magnitude scale of S4, and I mean the S4 designs pull very heavily from existing work, including a lot of SO. I mean, I think S4 might literally use the large aperture telescope mount as their mount in some proposals. So, yeah, so I'm doing that now. I'm working on the LAT specifically because this is a like 3 meter cryostat, right? The one that we have here is, maybe a meter long, but I don't know, 30 centimeters across. The large aperture telescope cryostat is huge and has like 13 optics tubes, each of them a little bit smaller than one of these in it. So it's a truly massive experiment. But it's sort of the next thing in CMB astronomy is basically to get more detectors on the sky, right? That's how you get more sensitivity. You decrease your integration times by getting more detectors. So, class has, you can see the number of detectors here, like 40 detectors at 40 gigahertz of, 500 at 90. So maybe we'll have 1,000 at 90, and then another few hundred, another 500 in each band at the high frequency. Simon's Observatory will end up with like 60,000 detectors on the sky. So it's like a jump. Now, SO isn't doing the largest angular scales the class is doing. The class is still complementing it by taking this other approach. The small aperture telescopes for SO are doing like a 10 by 10 degree patch really, really deep, trying to get to the B mode signal. And then the large aperture telescope is doing all of the really cool small angular scale science I didn't talk about over here in this plot. It's a lot of stuff like you can look at clusters through the SE effect, and you're really using the CMB as a backlight to understand the like distribution of stuff in the universe when you do that sort of small angular scale physics, and lensing, all that kind of cool thing. So yeah, that's what's going on with Simon's Observatory. We are going to maybe start deploying in the next year-ish. It depends a little bit on COVID delays, but the receiver I'm working on will be ready to deploy in the winter or spring sometime, which will be exciting too.
All right, and Michael, you've been patiently holding your hand up. Feel free to ask.
Thank you. So I was wondering about when the point you will reach where a non-detection of the B modes would correspond to a discovery. So basically, eventually you will reach the point where you're no longer limited by the technical statistical problems of measuring the B modes, and it's more of a ruling out theories type of discovery. So I was wondering if class is at that point, or if class doesn't discover anything, then there will just be a need for more follow-up.
Yeah, so I mean, anytime you set a new like upper bound on R, you're ruling out some theories, right? You just sort of, you've identified the problem of like, well, how low do you go before you say it's just not there? Which is, I think, a hard problem. Class is not, I would say, I mean, there yet. We are going to get to about point like 02, I think, is the limit we're going to set. You know, S4 will probably, I mean, it's a slightly different approach, right? But like, you know, S4 could probably do, it's planned to do better than that, right? One problem you do run into, though, is if this gets low enough, you see the lensing line here, eventually the B modes become enough below the lensing that the need to remove the lensing signal becomes challenging enough that it's not clear that it's technically feasible to do. Which isn't quite the same as saying that we rule it out, but it might like make the approach of looking at polarization for that purpose. You might rethink your strategy, right? Yeah, so that's sort of what class. So the other thing class is going to do is, so I frame this a lot around the B modes, but the E modes is actually, this large angular scale E mode pattern is really useful to measure. That's what's going to give us, say, the optical depth of reionization, which is important for like history of the universe reasons. It helps you, depending on your model of the universe, you can pull out the neutrino masses from that, which is nice. And that is going to be a cosmic variance limited measurement, right? You will not need to make another measurement of that once class is done. But yeah, the B mode, I mean, it's tricky, right? Like if S4 doesn't see B modes or whatever equivalent sort of next generation of this, other than maybe some thoughts from the edges, like, well, maybe this has a funky shape and, you know, S4 didn't look low enough in angular scale, so you need like super class to do it or something. I don't know what the field's going to be. I think we'll have to make some interesting choices about like what we think is feasible to do after that. Unfortunately, I don't think it's as simple as, oh, well, inflation is ruled out, or inflation theories involving gravitational waves are ruled out. Like, it's just, you'd have, someone will come up with an explanation for why, oh, actually, it should be 10 to the minus 7 or something, right? Like, which makes it tricky.
All right. I think we have time for one more quick question, if anyone has something they want to ask. But if not, then I wish to thank you again, Jeff, for joining us.
Yeah.
Getting to hear about your work.
Yeah, thank you for inviting me.
All right, in that case, everybody take care. Have a good rest of your week. And as I stated before, you can find on our website the link and list of previous talks, which we have listed in a YouTube channel playlist. So take care, everyone. And you too, Jeff, take care.
Thank you.